42. Three objects are connected on a table as shown in figure problem 542. The rough table has a coefficient of kinetic friction of 0.350. The objects have masses of 4 kilograms, 1 kilogram, and 2 kilograms as shown, and the pulleys are frictionless. Draw a free body diagram for each object. A, determine the acceleration of each object and their directions, and B, determine the tensions in the two cords. And then they give you the diagram. So the first thing I did was draw a free body diagram that mimicked the diagram they gave us, but now I'm adding all the forces. So first, I just want a note, just a general note that applies to all systems, but the acceleration of all objects are the same because it's all one system. So because they're all connected and it's all in one interconnected system, the acceleration of 4 kilograms is going to be the same as the acceleration of 2 kilograms, right? They're not going to like accelerate differently, and like one is going to pull more than the other. So that means that if we find the acceleration of, any one of these blocks, we find the acceleration of the whole system. And also you can tell just by kind of eyeballing it, if this is 1 kilogram and it's, straight in the middle of the table, it's just on the table, and this is 2 kilograms and this is 4 kilograms, because there's not any additional weight on either side or any other, factors, the 4 kilogram mass is heavier than the 2 kilograms. So we know that the direction of acceleration is going to go this way. So it's the 4 kilogram mass is going to pull it down because it's heavier than the 2 kilogram mass, meaning that the 2 kilogram mass is going to accelerate up. This 1 kilogram mass is going to accelerate to the left, and the 4 kilogram mass is going to accelerate down. So that's how we can use direction. So the directions in the acceleration, the direction of positive is always in the direction of motion. So I'm just going to put in the direction of motion, and then just up for this specific 1 kilogram mass, just for the normal force. So first, looking at the specific kilogram blocks. So for the 4 kilogram block, we only have two forces. It's just mg down and tension up, and it's positive in the down direction. For the 1 kilogram mass, we have the normal force going up, positive, mg going down, the tension going to the left and the other tension going to the right, because tension is always in the pull direction. And because we know that this is going to be accelerating in the leftwards direction, friction always opposes motion, so the friction force will be to the right. And finally, for the 2 kilogram mass, it's going to be tension up, mg down, and because it's going up, accelerating up, that's our positive direction. So what I did was I did the specific like the sum of the forces in the y direction for the 4 kilogram mass, the 2 kilogram mass, and then the sum of the x and the y for the 1 kilogram mass. And because you have a lot of unknowns here, t1, t2, and you also have acceleration as an unknown, you need 3 different equations. And we have 3 different blocks, so those are going to be our equations. So first, for the 4 kilogram mass, you only have forces in the y direction. So the sum of your forces in your y direction equals, so your negative tension plus mg equals mass times acceleration. We don't know what tension 1 is, and we don't know what the acceleration is. But we do know what the mass is, the acceleration due to gravity, and the mass. So if you plug that in, negative t1 plus 4 kilograms times 9.8 meters per second squared equals 4 kilograms times the acceleration, you're going to get a total of t1, tension 1, equals negative 4 kilograms times acceleration plus 39.2 newtons. And we'll need that later. That's why I boxed it. So for the 2 kilogram mass we have here, it is just T2, because acceleration is up, minus mg equals mass times acceleration. When you plug everything in, it's T2 equals 2 kilograms times A plus 19.6 newtons. And finally, for the 1 kilogram mass, so for the 1 kilogram mass we have in the x direction, which is really easy because it's not, lifting or anything, which means there's no acceleration in the y direction. So it's just normal force minus mg equals 0. So your normal force is 9.8 newtons. You need that because in order to get your frictional force, it's the coefficient of kinetic friction times the normal force, and they already give you in the problem that the coefficient of kinetic friction is 0.350. So for your sum of your forces in the y direction, it's T1, which is here, that's positive, minus T2, minus your frictional force equals ma. And so now T1 here, you plug in this. T2, you plug in this. And friction, you plug in this, equals ma. So now you're getting negative 4 kilograms times acceleration plus 39.2 newtons minus tension 2 kilograms times acceleration plus 19.6 newtons, minus friction, which is just the coefficient of kinetic friction, which is 0.350, times your normal force, which we solve for here, so 9.8 newtons, equals mass times acceleration. And the mass, you're doing the 1 kilogram block times acceleration. And now we can just add up all the like factors. So the constants will come together, the kilograms times accelerations will come together, and so in the end we'll get that 7 kilograms times acceleration equals 16.17 newtons, which means if you just divide it, acceleration is 2.31 meters per second squared. So that means that the acceleration of all of these blocks is 2.31 meters per second squared. But be careful that they're all in different directions. So because I indicated on the diagram, I didn't rewrite it, but just be careful that if you didn't indicate it on the diagram, you have to write that. And then finally, on to part B. All we do is, now that we have the acceleration equals 2.31 meters per second squared, to find the tensions, we just use our handy tension formulas that we already solved for, plug in 2.31 meters per second squared for A, and the tension of the first wire is 29.96 newtons, and the tension for the second wire is 24.22 newtons.